Okay, so what if we don't know the population standard deviation? When we did confidence intervals, I told you that we almost never know the population standard deviation. And when we were making confidence intervals, I showed you how you have to make a little adjustment to the formulas whenever you are working with the sample standard deviation instead of the population standard deviation. If you remember, in the margin of error formula, we used a t-score instead of a z-score. Well, if you're doing hypothesis testing, you're probably going to run into the same situation. You won't know the population standard deviation. You'll have the sample standard deviation instead. Well, you can still test your hypotheses. It's just you'll have to do what's called a t-test instead of a z-test. The traditional method and the p-value method that I showed you before could be called z-test because they were based on z-scores. Well, when you have the sample standard deviation, you're going to have to do a t-test, which involves t-scores instead. Let's look at this example here. A company believes that a new marketing strategy will increase the sales of a certain product. Right now, they sell an average of 6 products per hour. The new marketing strategy is employed in a sample of 41 stores. Those stores sold an average of 7.1 products per hour with a standard deviation of 3.6. With alpha equal to 0.05, can we say that the new marketing strategy increases sales? Okay, so let's state the hypotheses. So the company thinks that the new marketing strategy will cause the number of sales to go up. Right now it's at 6, so they think that the average will be greater than 6. The skeptic who comes along and says that the new marketing strategy will make no difference would say that the average stays equal to 6. So the null hypothesis is that the average is equal to 6. The alternative is that the average is greater than 6. When the experiment was done, the sample was selected, 41 stores. The sample average was determined, 7.1. And in this case, we have the sample standard deviation, S equal to 3.6. And that's probably what you'll have in real life when you study your sample. You'll get your sample average and sample standard deviation. As I've explained before, you'll probably never know the population standard deviation. Okay, well, if you want to analyze the data, when it comes to working with the t-distribution, that sample size of 30 is a magic number again. As long as the sample size is 30 or more, you can say that the sample mean would have this t-distribution. If the sample size is less than 30, then you have to know that the population is normally distributed in order to say that the sample mean has a t-distribution. Okay, but we draw the t-curve, which is a bell curve. Now, it's a bell curve that's maybe a little bit shorter and a little bit broader than a regular normal bell curve, but it's still a bell curve, so we go ahead and draw that. The t-distribution has 0 in the middle of it. Now, notice we're doing a right tail test here. Okay, so what I'm going to show you is basically the traditional method. Given the charts that we have to work with in our book, it's kind of hard to do the p-value method with t-scores, but the traditional method still works pretty well. So I'm going to shade in the right tail since I'm doing a right tail test, and I'm going to have to find the t-score that separates the shaded from the unshaded region here. So in order to do that, I'm going to go to my t-distribution chart. Okay, you might remember this chart that we saw before. And now we're going to look at the 2 rows that are that are called one tail and 2 tails. Now here we're doing a one tail test. Okay, it's a right tail test in particular. So we look at this row for one tail test and we find our alpha value, which is 0.05 in this case. Now we have to go to the rows for degrees of freedom. For confidence intervals, degrees of freedom was n-1. Well, for hypothesis testing, it's the same thing. Now, for other kinds of analysis, the degrees of freedom might not be n-1. It might be something different. But for confidence intervals and hypothesis testing, it's n-1. Our sample size was 41, so the degrees of freedom is 40. So we go down and eventually we find 40. And you might remember it was the second column where alpha was 0.05 in a one-tail test. So we have 1.684 is our critical t-score. And while I have this chart up, I just want you to notice that as your sample size gets bigger, the degrees of freedom here start to jump up, counting by fives and eventually by tens and even by hundreds. If the degrees of freedom you're looking for is in between two of the values in the chart, use the smaller number. So if we were looking, let's say, for 43 degrees of freedom, which is in between 40 and 45, we would go with the 40. Okay, but the degrees of freedom actually is 40 in this case. And so we have our 1.684 critical t-score. So I mark that as the t-score that separates the shaded and the unshaded areas here. Then I convert my sample average into a t-score. So sample average minus population mean divided by, this time, sample standard deviation over the square root of the sample size. So 7.1 is the sample mean, minus, if we assume the null hypothesis is true, like we do in a hypothesis test, we're assuming the population mean is 6. So 7.1 minus 6. And then the sample standard deviation is 3.6, and that gets divided by the square root of the sample size. Okay, so remember, subtract the two numbers in the numerator, divide these two numbers in the denominator, then divide your two results to get the final answer. So that would be 1.957. Now that t-score ends up in the shaded region because it's to the right of the critical value. And so what we would say then is that this sample average is far enough away from the population average, which would be in the center of this distribution, that we can go ahead and reject the null hypothesis. Okay, let's look at another example. The director of a hospital believes that her surgeons perform fewer operations than the national average of 211. A random sample of 15 surgeons had a mean of 208.8 and a standard deviation of 3.8. If the alpha value level of significance is 0.01, can we say the doctor's claim is correct? And we're going to assume that the population is normally distributed, which is kind of necessary for us since the sample size is less than 30. If we were not told that the population is normally distributed and the sample size is less than 30, like it is in this case, then we're kind of stuck based on what we've learned in this course. Okay, so in this case, even though the sample size is less than 30, we can proceed as usual because we're told that the population is normally distributed. Okay, so any z-scores or t-scores that we have to work with, all that will still work the same as we're used to. Okay, so let's state the hypotheses here. So the director thinks that the average is less than 211, so that becomes the alternative hypothesis. Saying that the average is equal to 211 would then be the null. When the experiment was done, the sample size was 15, the sample's average was 208.8, and the sample standard deviation was 3.8. Okay, since we're working with sample standard deviation, not population standard deviation, we're going to have to do the t-test again. So draw the t-distribution. 0, which represents the 211, is in the middle. And we're doing a left tail test here because of the less than sign in the alternative hypothesis. So shade a little bit of area here in the left tail. And we're going to find the critical t-score on this one. Okay, so the sample size is 15, which means the degrees of freedom is 14, and alpha was 0.01. Okay, so we're doing a one-tail test again, left tail test, that's just one tail. Alpha value is 0.01, and since the sample size was 15, the degrees of freedom is 14, so it looks like 2.624 would be the critical t-score. 2.624. Now that would be on the right side of this distribution. Because of the symmetry and because we're doing a left tail test, just call your critical value negative 2.624. Now convert your sample average into a t-score. Since we have sample standard deviation, we have to convert it to a t-score. So take the sample average, 208.8, minus what you would assume to be the population mean with the null hypothesis, that's 211. Then divide that by the standard deviation for the sample, 3.8 over the sample size, or I should say over the square root of the sample size, so the square root of 15. That gives you negative 2.242, which is somewhere between 0 and the critical value, so it's not in the shaded region. So this sample average is not far enough away from 211 for us to feel comfortable rejecting the null hypothesis. So our conclusion is Do not reject the null hypothesis. Okay, so we saw a left tail and a right tail t-test. Let's do a two-tail t-test to finish up here. A local pool claims that the average age of all its lifeguards is 23. You disagree. You select a sample of 12 lifeguards. Their average age is 24.6, and the standard deviation is 2.4. If alpha is 0.10, can you say that the pool's claim is wrong? Assume the population is normally distributed, which again is a necessary assumption since the sample size is less than 30. Okay, so if you think that this report might be wrong, then you're essentially thinking that the population average is not equal to 23, as was claimed or as was reported. Okay, there's nothing about the word wrong, like we said, that indicates higher or lower, so that's why you're using the not equal to sign, which is going to lead to a two-tailed test. The null hypothesis always has the equal sign, so in this case, the population mean equal to 23. When you did the experiment, you chose 12 lifeguards to be in your sample, found their average age to be 24.6. Sample standard deviation is 2.4. Now, when you analyze the data, since the population is normally distributed, even with a small sample size, we still know that the sample mean would have this t distribution. So draw the bell curve, which represents the t distribution. Okay, again, that bell is a little shorter and a little broader than a normal bell curve, but if we're just making a sketch, they essentially look the same. That 0 in the middle represents our null hypothesis value for the population mean, which is 23. Now a two-tailed test, we're going to shade on both tails. So I shaded both tails, and we're going to have to get our critical values. Okay, so I think we have degrees of freedom here. That would be 11. Remember, that's n minus 1, so 12 minus 1 is 11. And we said that the alpha value in this case is 0.10, so that's like 10%. So in our t-distribution chart, since we're doing a two-tailed test, we'll use the two-tail row, and we're looking at 10% for the alpha value, and degrees of freedom is 11. So 1.796 is the critical value. So on the positive side, call it 1.796. On the negative side, call it negative 1.796. Now convert the sample average into a t-score. So take the sample average, 24.6, minus what you would assume to be the population mean if the null hypothesis were true, which is 23. Divide that by the sample standard deviation, 2.4, over the square root of the sample size, so over the square root of 12. Okay, when you subtract the numerator, divide the denominator, and then divide those two results, you should get 2.309, which is in the shaded region, which means that this sample average is far enough away from 23 to say that the report is probably wrong. In other words, we feel comfortable rejecting the null hypothesis, which says that the average is equal to 23. Since the sample average was so far away from that, we say, you know what, that's probably not the case that the distribution is centered at 23. It's probably centered somewhere further out to the right where our sample average is located. So we reject the null hypothesis. Okay, so if you have sample standard deviation instead of population standard deviation, which in real life is going to be the case most of the time, you have to do a t-test with t-scores instead of using a z-test with z-scores. Now you can do the p-value method on with a t-test, but without the use of technology, it's really hard to get those p-values. So we really just go over the traditional method here for the t-test. But if you have some technology, some graphing calculators or some computer applications will calculate the p-value for you whenever you are doing a t-test. Well, if you want to use those technologies and get your p-value, you would just compare it to the alpha value like we did when we were doing the z-test. If the p-value is greater than or equal to the alpha value, then you would, or I'm sorry, if it's less than or equal to your alpha value, you would reject the null hypothesis. If the p-value is greater than the alpha value, then you would not reject the null hypothesis. Okay, but we'll primarily focus just on the traditional method here for the t-test.